in particle physics. And you will see that a number of concepts and notions have been developed in the course of studies of these particles. We started to discuss spine discovery, and oh, I have forgotten to switch on, right? With this discovery, and that was in Bristol, another methods have been used to visualize the tracks, namely emulsions. And emulsions, which contain silver bromide, under ionization, they form first free molecules of silver, and those molecules actually produce grains which can be visible. This is kind of non-trivial, right? This is chemical procedure, and to some extent for us, for particle physicists, this is empirical. That something, helps us to visualize the tracks. In a number of plates, the group observed quite interesting events, which look like, let me try to depict this. Of this type. Well, those are three different pieces of emulsion, and so they observe the tracks in emulsion of this type. The properties of these tracks are the following. So we have here, actually, you see three different tracks. Apparently something happens here in these vertices. And so let me denote this vertex A. Is B, and the tracks 1, 2, and 3. And the properties one can immediately recognize that for tracks 1 and 2, they become thicker. Probably you saw these tracks, this is in all the textbooks. I will try to use this discovery for my intentions, my goal in this course. The second feature is the second track has the same length approximately the same length for all events, and finally you can see that momentum and energy loss occurs in both vertices. Well, I can add that in different events, tracks 1 and 2 and 3 and the last one have different lengths. So what is interpretation of these events? So ask me questions if you want to have some additional information. Try to give an interpretation. Probably some of you already studied this. Right? So how you would interpret this? Again, when I will tell you you will say, okay, this is trivial, right? So the point is that when you see this in the first time, so this is how discoveries were done, it's by far not very trivial, right? So any idea how to?
Tracks left by the second tracks are basically the same particle because they have kind of the same wave, light.
Yeah, the same particle, yeah. But why the track has the same length?
The lifetime,
Yes, but then it's not enough to have the same lifetime because the energy should be the same, right? Because if you have particle with the same lifetime, then if you have higher energies, then the lifetime is bigger. Yes, of course you can say that those three are particles of the same type, and probably these are the particles of the same type, and these particles are of the same type. So, but what are these particles? How to explain this type of events?
Magnetic field?
No,
No.
they didn't use.
Next
They could use, yeah.
Those are charged particles?
But this is enough again, so that's enough to. Yeah, of course, these are charged particles.
And there's neutrinos to explain the laws of momentum and energy.
Well, yeah, so yes, one can immediately conclude that in these vertices, neutrinos are emitted in this and in this, right? So something, I don't know what is, how many, some neutrinos are emitted.
But why two types?
Huh?
Why do we have two types? Two vertices we have. Why do we have two vertices?
This is observation. So you see, they observe this track. So I explained how they use these emulsions. And among other tracks, of course, they see many other events which have easy interpretation. They observe these strange events.
Cosmic rays going in to the.
Oh yeah, I have forgotten to tell that again this discovery was in cosmic rays. So that's not artificial, it's cosmic rays. The source is cosmic. Probably I even said yesterday this, that the source is cosmic rays and the detector is emulsion. Yeah?
And how long is the tracks?
Well, I will show you actually a real photos of this track. I think this is maybe 20, 30 centimeters of this track. So small. You see this, no need to use any microscope. Ah, you see, it's not real, huh? You want to. Okay. But some of you had the courses in particle physics or nuclear physics. This is kind of trivial.
Maybe something is carried from A to B.
From A to B. Maybe some particle propagates from point A to point B.
Like maybe A triggers something at B.
No, just propagation of particle, which then interacts in point B, because there are 2 points of interaction somehow interaction. Okay, so should I help? Or how to give it as a homework? So the first is the track one is due to a new particle. Which eventually identified as pi. So this particle loses energy on ionization. Then stops and then decay. So it decays at rest. This is important. And I have shown here, so, you know, it's not accidentally, the track becomes wider, which is the signature of ionization energy loss. So for this, decay time of this particle should be bigger than the time of energy loss. Okay. Second, in the vertex A, this new particle decays with two particles in final state. One of them neutrino and another one a muon. So the second track can be identified as a track of muon. It's quite long, and also you see it becomes wider in the end, so which means that it loses energy on ionization. The fact that we have here two-body decay means that the energy of muon in all these events is the same, because this is two-body decay, and it is just determined by kinematics of this two-body decay. Okay? So the consequence is that energy of muon in all events is the same. So actually what happens is the mass of the pion is not much heavier than the mass of the muon, so the energy of muon is not half of the mass of the pion, but one can still resolve the energy and momentum conservation and find that the energy of muon and neutrino is the same in all these decays. So this is answer to your question. So here we deal with decay of muon, and since the energy is the same, then one can expect that the length is the same. Now, of course, so what happens here again? So let me write this. Still to keep all this. So the third is muon again loses the energy. Stops and decay. And again, to explain equal lengths of the tracks, we need to assume that the time of decay of muon is bigger than the energy, time of energy loss. As I already explained, this energy loss occurs in many small portions. So it's a process like a classical, essentially. Because if you would have decay just of muon in vacuum, for instance, you would expect different tracks, right? Because it's quantum process. And there's a probability that the muon decays faster or for a longer period, and therefore, it's just if you had in vacuum, you would expect different tracks. Okay? With average, of course, given by the lifetime of the muon. Now, since the length is essentially determined by energy loss. Energy loss is in small portions, it's like a classical process. And therefore, in all these events, you have the same lengths of the second track. Okay?
How can we say that the particle stops from just the picture?
Well, it becomes bolder and bolder here, the track. That is to some extent assumption.
Almost.
But because if it would be, if it would decay not at rest, then again you would expect that the length would depend on energy.
But for pi, how could we?
Oh, for pi, you see here, the tracks are very different in different events. So in one event it may be longer, and it depends on initial energy of pi. And energies were different in different events, and so you have different tracks. So what was really puzzling that this intermediate track had the same lengths in all the events. So that was puzzling. And to explain this, we need to kind of accept that here there is a decay, two-body decay of a particle. And so a single particle, so you have emission of muon in this case. And in all the events, then the muon has the same energy. Then the length of the track is determined not by decay, but by energy loss, by ionization energy loss. And so, since it's more or less a classical process, you have the same length to lose the energy from initial to zero, essentially. And in the point B, we have muon decay, and we have already studied this. So we have decay of muon into electron and to neutrinos. And this track corresponds to electron. And in fact, it could be seen that the track becomes thinner, which is a signature of radiation energy loss. So most probably this is the electron. Yeah.
Of course, it's not essential that the muon go at the same angle, like parallel lines. Or
at the same angle with what? No, it depends also on energy of. Okay, so that's at rest, and the angle can be quite different. So it can be any angle.
Any angle.
So you see here it's even like this. So here the angle is this one. Here's the angle like this one. This is the angle like this one. I just put this in kind of symmetric way.
I don't understand the part. Is it necessary for pion to be decay at rest, or is it also?
Yeah, otherwise you would have different energies of muon, and therefore it would be different lengths of the trajectory. Because here, initial energy of muon is the same. And then you have energy loss on ionization.
Because of the velocity that it gets, we would have longer lines. Although the lifetime.
Well, you will have you need then to lose bigger energy, so you will need a more travel time to lose more energy. And of course, it also depends on velocity. True, because ionization quite strongly depends on velocity. So it's important that you have the same initial energy of muon at the production.
So. How is it possible that pions travel all the way until they stop and then decay?
Well, this means that gives some bounds on lifetime of pions. So it should live long enough.
So long enough that all the pions that is also.
So that this pions actually stops before decay. Okay. Well, actually. Nothing is complicated, right? So actually, all the kind of items you knew already. You know, properties of energy loss. Actually, this is why I devoted again the lecture, because now you understand better what's going on and how that was discovered. Okay.
People at this point believes that neutrinos are existing.
Neutrinos are existing.
Neutrinos are real.
Yes, yeah. Well, they were still not discovered. However, already attitude changed, and yes, people also already some other particles have been discovered, and that was more acceptable that another particle exists. Yeah. So this interpretation they used.
So these all events that we observed, like a ghost edge height vertices, are somehow always related to neutrinos and somehow always related to the weak interactions.
Yes, yeah.
And
so you can say these are weak interactions and neutrinos. And still again, now if say in the modern experiments, people observe some missing energy. The first idea is that these are neutrinos, when neutrinos are produced and things. So actually, we don't know. Some speculative or some kind of hypothesis that some other particles which are neutral exist, but they are not discovered. So neutrino is, in this sense, is exceptional. Of course, we have neutrons or some other neutral mesons, but then eventually they have a strong interaction, so we can see them. Okay, so now let us discuss theory of pi decay. So I didn't, of course, present all the analysis, but clearly people tried first to use known particles to explain these events, and that there was no way, known particles couldn't work. So one can try again that muon is in initial track, but then you cannot reproduce this picture. These two tracks. Theory. So what we have, two-body decay of pi into muon and neutrino. So this means that we deal here with weak interactions. And again, we see here appearance of two leptons, the pair, right? Muon and neutrino. So, looks like these interactions in which leptons, charged leptons appear with neutrino, which is similar to what we had in the case of muon decay, and also similar to beta decay, right? So, using analogy to what we learned already before, we can write the Hamiltonian responsible for this decay. And let me write this in this way. So G, let me first just put G without anything, the square root of 2. Then I can assume that these leptons interact through currents, as we already had before. So yeah, trivial observation. So I put here leptonic current. And I multiply by some other current, which I call hadron current, which is related to this pi, which is, if it is Yukawa coupling, is strongly interacting object. So this current is what we had already before. It's muon, gamma nu, and then I can assume that it has the same Lorentz structure. So I will write, because that's what is finally has been established. Now this current, I don't know what is this a priori. However, I can extract many things just using this general expression. You will see that I can essentially compute the probability of the decay. So I don't know what is explicitly this. I use here, of course, Lorentz invariance. If I have here some object with mu, then I need to have something here with mu. And so I can say that this is some operator which carries the index mu, Lorentz index mu. And for time being, that will be enough. So I assume this structure of muon current in analogy is what I learned already before. Using this Hamiltonian, I can write the amplitude of the decay, which is given by matrix element. I have in final state muon and neutrino, then Hamiltonian, and pi in initial state. Right, so I need to compute this matrix element, and then of course compute moduli square of this element, and this gives me the probability, this usual stuff. Now inserting Hamiltonian, I can rewrite this, so I can continue as G square root of 2. Then what I can write is kind of factorize this, because here a Hamiltonian factorizes. I have two parts of this Hamiltonian. And so this one is responsible for the structure, and this one should actually take care about pi, whatever happens with pi. So therefore I can write this as a product of two matrix elements. One contains leptonic current. Okay, so once I started to write that, then I should write here muon and neutrino. And in initial state, I have no leptons, right? I have just pi. And therefore, it should be matrix element between 0, vacuum, and in final state, I have muon and neutrino. And the second one describes what happens with pi. I put here this current, which is hadronic current, and this wave function of pi. So, this hadronic current, whatever it is, operator, annihilate pi. So we have pi in initial state, and there is no hadrons in final state. So this current, leptonic 1, produces from 0, from vacuum, the pair muon and neutrino. Muon and neutrino were not in initial state. Okay? Now, this we know explicitly. This we know because we know what is the shape of the current. We know what are the wave functions of muon and neutrino, and we can use plane waves if you want. Right? Okay? So we can use, of course, plane waves because this muon and neutrino just freely go out of from pi and decay. So this we know explicitly. Can compute. This we don't know, because we don't know what is this current and how it can be expressed in terms of operator of pi or wave function. However, we can say a lot of things without even explicit knowledge of this operator, and we can write that the matrix element between pi and 0 should be what? We can use Lorentz covariance, right? So we have here index mu. Then what is staying on the right-hand side should also have index mu. Eventually, all these computations of matrix elements give us some expressions in terms of kinematical variables, right? I mentioned already. So eventually, what we compute cross-sections, probabilities, and they are functions of kinematical observables. So what you would write here on the right-hand side? Tell me, how you would write this matrix element using covariance?
Maybe we can boost the center of mass.
What?
We can boost the expression.
No need to do this. Just using Lorentz covariance, knowing that after all, computations should be to give me something with index mu, some kinematical variable with index mu. So what we should write?
Momentum.
Yeah, right. So simple, right? And no way you have to have something else, because the only what is staying here is pi. The only kinematical variable is then for momentum of pi. And so this is like a completely precise statement. So that should be proportional to p mu. And then we put some constant here, f pi, which is called constant of pi and decay, or pi and decay constant. Which actually plays a very important role in physics. The size of this coupling, first let us estimate dimension. So what we have here, remember we estimated dimensions of current in the case of two fermions in initial and final state, and that was mass in the third power, right? Here we have bosonic fields. So here is bosonic and this is bosonic state. Oh, I didn't mention, but clearly if you have this type of the decay, the spin of pion should be integer, right? And the simplest possibility that spin is 0. That was then confirmed. So this is, well, actually the same anyway. So if it is an integer spin, the dimension is mass over 1/2 smaller than dimension of fermionic field, right? So here we have 2, and therefore dimension of this object should be mass squared, because dimension of such a matrix element like here for fermions is mass cube, or mass in the cube, in the third power. And here it should be mass in the square power. So this means that f pi should have dimension of mass. And numerically, it turns out that this is approximately equal to the mass of the pion, and something like 130 MeVs. I didn't also mention, but from these studies from kinematics, and knowing what is the energy of neutrino, one can estimate a mass of the pion, and that was 140 MeVs. So this simple kinematics. Okay, because you can measure what is the energy of muon, right? Because you know what the tracks, what is the length of the track, you know what is the energy loss, and therefore you can find from here the energy of muon, and then you have two-body decay. It's easy then to reconstruct what is the mass of pi. Okay, so this is already very important input, and we can continue with computation of our matrix element. So notice that the momentum of pion equals momentum of muon plus momentum of neutrino. Using this, you can write the matrix element as GF square root of 2, then F pi, which comes from this when we insert here, right? And so then I'm writing here, because this is P momentum of pion, and then I use this expression as the sum of momenta of muon and neutrino. And then what I will get is the following. I have P nu mu plus P mu muon multiplied by what actually comes from leptonic matrix element. And now what comes, let me write explicitly in terms of spinors. The spinor which corresponds to muon, gamma muon, 1 minus gamma 5, and then spinor which corresponds to nu. Well, the wave function actually is given for this fermion by spinors, right? 4 spinors multiplied by exponent, right? Which is plane wave. Well, I omit these plane waves because eventually we are computing moduli of matrix elements, so they will disappear, this exponent. So I just keep spinors, 4 spinors. Okay, agree? So now you can notice the following feature. So we can combine this P mu with this gamma mu. So we have 2 terms. So let me continue. We have GF square root of 2 F pi, and here we have U muon. And then I combine P mu with this gamma, and so what I will get is P mu slash, oh, I need to put here mu. Sorry for this confusion with indices. So this is as usually P mu gamma mu. Right. I could use different Lorentz index. 1 minus gamma 5 plus I combine this nu with also with this mu. The second term will be u mu. 1 plus gamma 5 p nu u mu. And let me explain again. So we have two terms. When we multiply this by this current, this block, and this one multiplied by this block. And now what I have here, I have combination of this 4 momenta with gamma mu. And so then I will get this P slash. You use this probably, right? So sometimes people are using this HEP for notation, so all this. Yeah? Here is a plus. I change here minus to plus, not accidentally, because gamma mu is staying here, and I put this gamma close to neutrino, and therefore I have plus here. Because I don't know, you probably studied this gamma 5 has this feature of antisymmetric property. So when you permute gamma mu with gamma 5, you have change of the sign. So I did this permutation to attach this P slash for neutrino with corresponding spinor, and attach this with spinor of muon.
At the first term.
In the first term.
At the end.
You know.
Oh yeah, sorry. I need to write here, yeah. Unions. Thank you. Focus. Okay? Now what I do, I'm using Dirac equation, right? So when this guy acts on this, what I will get u mu, the mass of mu, right? And here I will get mass of neutrino, u mu, right? Just as a consequence of the equation. Okay, so then I continue. What I will do, I will neglect this mass of neutrinos. I will neglect this term because mass of neutrino is much smaller, very small in comparison with mass of the muon. And I will get expression g square root of 2 m mu f pi u mu 1 minus gamma 5 u nu. So, and then it is routinely to compute decay rate or probability in the unit of time, and that will be gf. Oh, sorry, I don't want to put here f square, g square, 8 pi. Again, these are factors which appear from integration of space volume. Then, of course, it will be f pi squared, because we square this mass of the muon square. And, of course, it should be mass of pi or something like this, because of first dimension. And, of course, it should be proportional to energy release in the process, because if there is no energy release, then probability should be 0. And actually what is staying here is 1 minus m mu square over m pi square square. So, of course, if m mu approaches m pi, we will have no phase volume, and you should have this suppression factor. Okay? And just on dimensional ground, you need to have here something of dimension 5, right? So we already established this. So that should have dimension 5, and this F pi has dimension of the mass. This is mass square, and that it should be mass of pi. Because if mass of pi is 0, then no decay at all. And this also you can more or less understand. Again, if mass of muon approaches mass of the pi, and then you will get a 0 energy release, and therefore probability should go to 0. Okay? So you see, we almost derived, we kind of derived essentially the final expression for decay rate of pi without doing sort of explicit Feynman rule computations. So this is the power of this analysis. Okay? So just using some symmetries, covariance, we used also Lorentz, covariance and dimensional arguments, you get this expression. And also physics, because you know we picked up this factor and mu. Yeah.
We use the equation there. Are we assuming that they are like free particles?
Yeah, of course. Yeah, this is what I was saying. Yeah, you have. So you have pi, and then you have decay into nu and mu. So then muon then interacts with medium, but in the initial point we have this decay into free particle. Questions?
So what is the coupling between the initial particle and the resulting particle? Is there a coupling between them, or?
Yeah, we have written Hamiltonian, which actually describes this coupling.
But in the Hamiltonian, when we put the vacuum in middle.
No, in vacuum we have Hamiltonian in vacuum. What was written is Hamiltonian in vacuum as a product of two currents. So that's actually what describes elementary interactions.
So it's look like that we have independent matrix elements and.
Yeah, we split it, factorized total matrix elements in two parts. At least in the lowest order, this is possible in the lowest order in perturbation theory. Okay?
This G is close to G Fermi?
So I'll come to this. Let me make a few comments. Remember I said that in the case of muon decay, we just put mass of the muon into the fifth power. Remember when we did estimation. Here it would be wrong, because you see what is staying here are different stuff, different masses. This F pi, which a priori can be quite different from the mass of the pi. Here we have mass of the muon, and here we have mass of the pi. So this is the case when very naive dimensional arguments do not work, because naively you would say, okay, we'll put here mass of the pi and the first side. However, things are more complicated. And here we have two-body decay. So what is important that we have two-body decay here, and with this Lagrangian or Hamiltonian of certain type, and that leads to appearance here of the mass of the final particle, mass of the muon, in contrast to decay of muon, when we neglect masses in final state. Now, this actually related, and you will have later the exercise. You can prove appearance of this muon just using angular momentum conservation in this decay. So this is related to, eventually you can trace this from the angular momentum conservation, appearance of this mass of muon. Okay. Now the question I want to ask you, what are other decay modes of pion? So we discussed decay into muon and neutrino. Can it decay into electron and neutrino? Do we have this type of the decay? So which decay is the main one, what dominates? Yeah.
We just compute the amplitude the same way. We see the probability.
So, what is the probability of this decay?
It's mass of pi to the 5th power, because the masses in the final state are not that much.
No. Other suggestion? Again, I told you that the appearance of mass of the muon here is not because of this kinematic reason you are talking. So that what takes care about the phase volume. So, of course, in the case of electron, you will have much more phase space. You have more energy release, right, and kinetic energy, because mass of the muon electron is much smaller. So naively, you would say, okay, that should be even more probable decay, which is not the case.
When we do the probability calculation, just we replace the mass of muon with mass of electron.
Right, right. So
it will be very low.
right, because if you repeat the same computations, but with electron, you will get again appearance of mass of the electron as the consequence of Dirac equation, right? So the same. So here you will have the same, that you can neglect, of course, this factor, but you will have that gamma is proportional to the mass of the electron, to electron mass squared. So counterintuitively, you would expect bigger phase volume in the case of electron neutrino. But because of this kind of fundamental thing interferes, like angular momentum conservation, things like that, so you cannot do anything about this, eventually, so it's physical reasons. So we made these computations. We have found explicitly how this factor appears through these computations. But again, you can find out this just using angular momentum conservation. These rules automatically take care about this when you do this quantum field theory computations. But from physics point of view, you can again identify appearance of this factor as the result of angular momentum conservation. So this means that such a decay would be almost 5 orders of magnitude less probable. So decay of pi into muon and the corresponding neutrino dominates. This is main mode of the decay. Actually, this plays extremely important role in all these neutrino oscillation experiments, because we know that the state of neutrino which is produced in pi decay is almost muon neutrino associated to muon. So we'll discuss this later. Okay. So let me say a few words about implications of this discovery and the theory of pi decay. Again, this is feature of two-body decay. In the case of three-body decay, you would not have this factor which is proportional to the mass of particle in final state, because in the case of three particles in final state, you will manage to satisfy angular momentum conservation without specific bounds. Yeah.
Is it that in the previous decay where muon decays into 3 particles, we only have the muon mass to the 5th power?
Yeah.
Without any angular
Without
momentum?
any kind of problem. Yeah. You can
So,
start.
although the final state particles might have very, very small compared to the initial particle mass, in the case of a two-body decay, we need to consider them
Yes. Right.
as
Exactly.
to the
Exactly.
square
Exactly.
round.
Yeah. Yeah. So what are implications of discovery of pi? Consequences. So first is the lifetime of pi as 2.6 10 to the minus 8 seconds. This is 2 orders of magnitude smaller than the lifetime of muon. So pi decays shorter, decays quicker. And it is for this reason, pine was identified as Yukawa particle. Particle which is responsible for strong interactions. So in Yukawa theory, in the previous years I also discussed this Yukawa theory, but this time no. You can estimate what should be decay, and Yukawa estimated what should be decay time of this Yukawa particle. And it was something like 10 to the minus 8. And when it was established that muon decays with a lifetime 10 to the minus 6, 2 orders of magnitude longer, that was indication that muon, previously discovered, is not Yukawa particle. So with this, everything is okay. So you can identify this with Yukawa curve. Second is that mass of the pine is approximately, as I said already, 140 MeVs. So what is special about this quantity? Look how many things actually come out of this. This mass is much smaller than the mass of the proton or neutron, and it's also much smaller than the mass of other mesons discovered later, like K meson, like rho meson. So natural mass scale would be around GeV for this type of the particles. But for pines, for some reason, the mass is much smaller. So how it was explained? It was explained that behind all this, there are so-called chiral symmetry. I will come this after we will discuss quarks. So this is easy, although I can also introduce this in terms of mesons as it was actually originally developed. So the chiral symmetry is related to the symmetry of rotation of right-handed components of particle quarks, right? And left-handed components of quarks independently. And so the theory or Lagrangian of interactions is invariant under this rotation. This is what is chiral symmetry, roughly speaking. So the statement is that this chiral symmetry is spontaneously broken. You don't understand this quite well, I can admit, but just to have an idea of how many things come from this discovery. So it is spontaneously broken. Which means that the vacuum expectation value of pine field is non-zero. So the lowest energy state of the system of pines, actually not only charged pines but also neutral pines have been discovered, and one of these components which belong to the system has non-zero vacuum expectation values. Okay. Then according to Goldstone theorem, you see how many things? According to Goldstone theorem, once you have spontaneous symmetry breaking, global symmetry breaking, you have appearance of massless states. And so pines have been identified as Goldstone bosons of this spontaneous breaking of chiral symmetry. So this is the reason why their masses are, in the first approximation, zero. But non-zero masses appear as the result of explicit breaking of this chiral symmetry. And this explicit breaking, as we now know, are related to the masses of quarks, of light quarks. So this is just kind of lateral comment, but just saying that so many things come from very simple observations. So a single observation, but a lot of stuff comes from this. So not only this, it was established that there's a relation between our decay coupling constant and then Ga and mass of the nucleon. And Ga, this is what we have seen, is 1.23 in axial vector curve. So on this basis, chiral perturbation theory has been developed. You see how many things, and actually Weinberg started his career working on this Pine physics, spontaneous symmetry breaking and all those things. So this is how actually he knew about this spontaneous symmetry breaking, and when Weinberg has written his paper, actually he thought, why not to apply this, to, I don't know, to get masses of W boson and Z boson. So that idea led to Nobel Prize, as you know, and establishing of the standard model. Again, this is just to illustrate that it looks like, okay, some particle has been discovered, so what? But so many things are behind, like we discussed already, discovery of muon. Questions? Yeah.
The attached hadronic current from fire. I can't now really distinguish between hadrons and leptons.
Yeah, so yeah, that's a little bit an advance because people didn't make this clear identification before. We actually refer to hadrons as strongly interacting particles. So particles which have strong interactions, and Pine has strong interactions. So he interacts with, by definition, Pine is responsible for a nuclear structure according to Yukawa. And now we understand these things are more complicated, but in some approximation you can say this. And these interactions, which are actually responsible for nuclear structure, we call them strong interactions. So that's really Pine should have strong interactions with proton and neutron to keep them inside the nuclei. So those are particles, strongly interacting particles. And once we are saying that Pine is Yukawa coupling, which means that this is strongly interacting particle. Okay, now let me discuss discovery of another extremely important particle. And you will see how many things come from, eventually from studies of these particles. And those are K mesons of counts, discovery of counters. So K mesons have been discovered in 1947 in Manchester. By the cosmic ray group, and the leaders were Rochester and Butler. Rochester and G. Butler. The source was cosmic rays again. And the detector was cloud chambers, so we kind of, in this sense, back to cloud chambers. So in the cloud chamber, they saw some events which look quite interesting and different from what has been observed before. And these are so-called V events. So next time I'll certainly show you the slides, and you will see how all these events look like. So again, in the cloud chamber, they saw events of this type. Well, actually, there were curvatures here, so that's of this type, most probably. And they were identified as the pair of pi plus and pi minus. So that some particle, which is not visible decays into pi plus and pi minus. Also, events of the type when some new particle or some particle left the track produces pi plus in this way, and also two gammas, two pair of gammas. Something like that. And then the interpretation of this event was that that comes from, sorry, that's a plus and minus. We cannot see gamma, so it's a plus and minus. So this plus and minus come from gammas, and these gammas come from pi 0 decay. So what you have here, decay of some particle, x, into pi plus and pi 0. These two pi 0 decays into two gammas. What's interesting that pi plus, what we discussed pions, charge pions, right, before. And when I was saying 2.6 10 to the minus 8 seconds, this is decay of pi plus and pi minus. But apart from pi plus and pi minus, pi 0 has been discovered, which has very close mass to this pi plus and pi minus. And for pi 0, the dominant mode of decay is this one, because this is due to electromagnetic interactions. And so decay time is 10 to the minus 17 centimeters, 10 orders of magnitude almost faster.
This is the only way to detect pi. Is this the only way to detect neutral pion? Because
that's what we are doing. So we can observe in this way two gammas, and then we can reconstruct the invariant mass. We can actually, knowing energy and momenta of photons, we can recover what is the mass. Then if it is mass of the pi, then we say, okay, this is pi 0. Yep. So in these gammas, as we discussed already, produce plus and minus pairs in the field or electric field of nuclei. So it's not in free space. So they produce this plus and minus. And that has been observed. Now, not only these events when some new particle produces muon and nothing more here, and that was interpreted as decay of this x into muon and corresponding to neutrino, similar to what happens with spines. So from here, assuming this two-body decay, you can estimate the mass of this particle, and it happened that the mass of this particle x, which is identified, let me call it x already as count k. The mass of k is approximately 500 MeVs. So, in this way, new particle has been discovered with a mass around 500 MeVs, and this particle has been called strange particle. Let me write precise mass. So precise mass of Mk is 493.7 MeVs. So it's 4 times heavier than pi. So these particles have been called strange particles. And they called strange particles for one reason. So first, it was also measured that the lifetime of K is 1.2 10 to the minus 8 seconds. And this event has been interpreted as decay into neutrino, which means that we deal with weak interactions. And this lifetime corresponds to really typical lifetime of particles, time of weak interactions, because strongly interacting particles and decays due to strong interactions have lifetimes 10 to the minus 20, 22, 23 seconds. Much, much, much faster. So long life indicates weak interactions. Interpretation of V events was K0, go to pi plus and pi minus. So that event is when we have neutral K meson, which decays into pi plus and pi minus. So we are discovering family of new particles, K mesons, which have the charge components and also neutral components. So V events, and also you can use measure pi energy at momenta and to find what is the mass of decaying particle. So this event, that event, so this testifies for existence of new particles. So that is also charged particle. That's K plus, which decay into pi plus and pi 0. So what is interesting and what is important, here we deal with decay of strongly interacting particles. So pions are strongly interacting particles, and still decay rate is very slow. So decay, the time is too big for strong interactions, in spite of the fact that all the particles involved here are strongly interacting particles. So they are strange because they decay due to weak interactions. And on the other hand, they are produced in strong interactions. So how do we know that they are produced in strong interactions? We know this because the number of events of this type is comparable with the number of events due to pions. Okay, so we know that pions are strongly interacting particles. Pions are produced in strong interactions of, say, initially coming protons or nuclei in the atmosphere, so these are secondary. But what has been found that the number of events with kaons is not much smaller than the number of events with pions. So if you would say that this is produced by strong interactions, this is by weak interactions, you would expect, say, 10 orders of magnitude smaller number of events. Of course, number of K mesons events was smaller, but that was just explained by difference of masses. So the mass of the kaon is 3 times or 4 times bigger than the mass of pion. Of course, that produced some suppression of production rate. But otherwise, the strength of production of K mesons is the same as pions. And pions are produced by strong interactions. So this is the origin of name, strange particle. So we call this strange particle. Of course, this is not like the particle has a really strange form. It's strange because the observations are strange, right? So particles produced in strong interactions, however, decay in weak interactions. Although kinematically, this process could be due to strong interactions. All particles are strongly interacting particles. So that was amazing. So why it is so slow? Do you have some idea how you would explain this? How one can explain? And just from this observation, a number of concepts emerge. So already by that time, people discussed three types of interactions: weak interaction, strong interaction. So weak interaction is responsible for beta decays of processes with neutrinos. Strong interactions responsible for structure of nuclei, and electromagnetic interactions. So three types of interactions. These interactions have different conservation laws. So we can introduce some quantum numbers, or set of quantum numbers, including electric charge, but also some other quantum numbers. The concept is the following, that some interactions respect some quantum numbers, but violate some other quantum numbers. Electromagnetic interactions are most symmetric in a sense because they conserve electric charge, but also other characteristics. But also strong interactions are quite symmetric, and they respect or conserve various quantum numbers. So that one can introduce quantum number which is conserved in some interactions but is broken by other interactions. And usually weak interactions do not respect a quantum number, so they like to break, as we will see, quantum numbers. So then the interpretation or explanation of these strange properties is the following. K mesons care non-zero value of some new quantum number, which is called strangeness. So that strangeness of K plus equals strangeness of K0 and equals 1. And strangeness of antiparticles has minus 1. So strangeness of K minus equals to strangeness of K0 bar equals minus 1. So here, in contrast to pints, where we have just one neutral component, pi 0, there are two components, two neutral components, K0 and K0 bar, and they differ by this new quantum number, by strangeness, so they have opposite strangeness. All other particles have zero known strangeness. So pi has zero strangeness, proton and neutron, so they have zero strangeness. First, so we introduce a new quantum number. And we will see that the story will appear again and again when new particles have been discovered. Second, we are saying that strangeness is conserved in strong interactions and electromagnetic. So what does it mean? So strangeness, we introduce it as additive quantum number. So if you have system of particles, then you can define total strangeness as the sum of strangeness of all the particles in a system. And conservation means that the total strangeness in initial state equals total strangeness in final state of the process. For this reason, K-mesons should be produced in pairs. So they are produced by strong interactions. For instance, proton interacts with nuclei and produce K plus, K minus, and plus the rest. It could be a number of other non-strange particles. Strangeness of initial state is 0, right? Because these are non-strange particles. And strangeness is conserved, and therefore in final state you should have strangeness 0, and in fact this is what happens. This has strangeness plus 1, this has strangeness minus 1, and therefore total strangeness in final state is also 0. Right? Total. So for this process strangeness is conserved, and therefore it can go through the strong interactions. Finally, we are saying that K mesons are the lightest strange particle. So all other hadrons or other particles which are lighter than K have strangeness 0. What does it mean? This means that decay of K meson should go with violation of strangeness, right? Because particle can decay only to particles which are lighter, so the sum of masses should be smaller than. And so for this reason, K decays are with violation of strangeness. So, for instance, K plus can decay to pi plus and pi 0. So here's strangeness 1, and in final state we have strangeness 0, and therefore this decay violates strangeness. Therefore, it cannot be due to strong interactions, because we are saying that strong interactions conserve strangeness. So that cannot be due to strong interactions. Weak interactions break strangeness. And therefore this decay can proceed via weak interactions. So also strangeness is conserved by electromagnetic interactions, and therefore this decay cannot be due to electromagnetic interactions. So the only way to have this decay is to have it decay due to weak interactions. And therefore we have this long lifetime of these particles.
This one is ZM.
What?
Conserved in strong interaction and electromagnetic interaction.
Right. Is conserved, yes, sorry, and electromagnetic. Right, thank you. So it's conserved in strong and electromagnetic interaction. Yeah. And it is violated in weak interactions. Well, it's a simple, right, in a sense. So we have some particle which is produced by strong interactions because and it has because you can satisfy kinematics and you might have these processes. However, as far as decay is concerned, and you are saying that K is the lightest, this is important, the lightest strange particle, then it can occur only with violation of this quantum number, strangeness, and therefore it can proceed only with due to weak interactions. Yeah.
But is it possible to have a strange particle which is heavier than K meson, but there's particle which has not a strange number in between them, and is it possible to that particle to decay to those particles?
Yeah, so this is what I want to say next. After K mesons, some other strange particles have been discovered with a bigger mass. For instance, K star, this is notation, with a mass 892 MeVs. And this particle, kinematically, this is not the lightest, and therefore it can decay with final state where you have K meson plus pi. Now, here, strangeness is conserved. Kinematically, this is allowed, and therefore this will go via strong interactions. And the width is very big. It's 10 to the minus, sorry, the lifetime is very short. It's 10 to the minus 21 seconds or so. Also, baryons, or some analogy of proton and neutron have been discovered, like lambda baryon, which has mass 1045 MeVs, and it can decay into another strange particle, which is sigma plus pi. So it's another decay. And the lifetime here is 10 to the minus 23 seconds. And we will discuss the theory of K decays and appearance of another important concept of mixing in the next lecture. Well, actually, you will see that these K mesons played a really important role, because it is study of K meson which led to introduction of parity violations. The parity violation has been kind of observed because of decay of K meson. And then CP violation has also been discovered in the processes with K and decay of K mesons. So just single particle led to so many concepts: introduction of a new quantum number, introduction of mixing, CP violation, P violation. Questions?
By this time they thought about why there exists this quantum number, which symmetry leads to this, or they didn't thought about that.
Well, I think that started quite soon, because people start to make classification of particles. Maybe not immediately when after this strangeness has been introduced. Frankly, I don't know how, if people who actually invented all these things, if they thought about the symmetry or not. So, but essentially that came from classification of particles. So by that time already isospin has been observed, and I think it was kind of more or less obvious that they could think about some new symmetries behind.
But this, all these quantum numbers, the strangeness, and the other things, charm and things like that, explains with the quark model.
Yeah.
So it's then it's a matter of quarks transforming into another quarks in this new model.
Well, you see, eventually, once you started to speak about this. So we are saying that strong interactions respect this symmetry, right? Which means that the strong interactions, so they respect this quantum number, which means that the strong interactions have some certain symmetry. And this symmetry is related to transformations of quarks, as we now know. So we had U quark, D quark, and now we should introduce S quark, strange quark, and then strong interaction Lagrangian is invariant under transformations of this part when you have permutations. I will discuss it. I don't want to. More questions? Okay. So then, who is next in line? I want to talk. I want to talk to you and to you, right? And tomorrow you will have exercise chambers.
Another question. Regarding to what we saw about there is only 3 generations of leptons. I read that, for example, the Z0 boson decays almost in all the particles.
Yeah.
So if there exists another generation, that means that the other neutrinos will be very, very large mass particles.
Yeah, exactly.
Is that enough to say the reason that's why only 3 generations?
Well, you know, now we have, so about the 4th generation, right? So that's almost excluded, I should say. But at least usual chiral generations are similar, are excluded. One reason is that you need to have very heavy neutrino, and but then you need to take into account different corrections, and now we have this. And then these particles from the 4th generation cannot be too heavy because we have this scale of Higgs web. And we already checked that the mass scales even above, say, TeV, and we haven't observed any particles which could be associated to the next generation. Okay.